Okay. Good morning, everyone, and welcome to another session of Science Chronicles. We hope you're as excited for today's session as we are. This webinar is organized by IPKI in collaboration with the EcoScience Foundation. For those of you who are new here, the EcoScience Foundation is a specialized agency of the Economic Cooperation Organization, an intergovernmental entity with 10 member states, including Afghanistan, Azerbaijan, Iran, Kazakhstan, Kyrgyzstan, Pakistan, Tajikistan, Turkey, Turkmenistan, and Uzbekistan. Its mandate is to promote science, technology, and innovation among the ECO member countries. IPKI is an organization committed to making the world a better place by promoting science education, fostering intellectual curiosity, and bridging gaps in access to quality learning opportunities. Today's session takes us on a journey through one of the most transformative revolutions in human knowledge, the rise of quantum mechanics. This talk will trace a century of scientific breakthroughs while also looking ahead to the frontiers of quantum information science. We are extremely honored to have with us Professor Dr. Farhan Saif, a renowned figure in Pakistan's scientific community. Dr. Farhan Saif is a tenured professor at Quaid-e-Azam University, Islamabad. He earned his PhD in Germany and completed postdoctoral research at leading institutions, including the Ulm University, Germany, University of Arizona, USA, University of Electrocommunications, Japan, and the University of Sao Paulo, Brazil. His earlier work includes pioneering contributions in atom quantum optics, quantum computation information, and dynamical systems, nano-electro-optomechanics, such as the creation of quantum bullets, development of quantum channels for communication and cryptography, quantum recurrence microscope, quantum data storage with 100% efficiency, switching devices, and single-photon quantum transistor. Please join me in welcoming Professor Dr. Farhan Saif.
Well, assalamu alaikum. It's my
Yes, Dr. Saab, you can continue. Thank you, sir.
Assalamu alaikum. Well, it's my pleasure to be here and present my work. So here I'm going to talk about the 100-year journey of quantum mechanics, and the title of my presentation is From Heisenberg to Quantum Computers. So I would be presenting the important innovation in the subject right from the very beginning. And then I'll be trying to connect these innovative ideas with important applications and technology which has emerged. So if we want to talk about quantum mechanics, it's a subject which talks about interaction between matter and field. When we want to understand field, it's just the optical radiations around us coming from various different sources, and we have a long history of this, starting from human conscious, how light plays a role in our life. So the first focused work was coming from Hatham, who is also known as Al-Hazan in European scientific community. And he wrote exactly 1,000 years back 7 chapters of his book, Kitab al-Manazir, where he explained the properties of light and how we can use it for various different purposes. He changed the understanding of previous Greek scientists that was particularly connected to the vision theory, how we really view things. So when we want to talk about present-day technology, present-day understanding, so it came from the work of Planck's, and that work of Planck actually solved a 1,000-year-old puzzle whenever it was a question about the nature of light, its particle nature, or its wave nature. So it was always coming with different views. For example, Newton came up with an understanding that light should be composed of particles. But afterward, the theory of diffraction, interference, suggested that it should be a wave rather than particle nature. So the work of Planck actually became very important in that sense, because he settled this discussion and he presented that the light made by the discrete particle. He named them as light quantum of light. And then that was his first understanding. He presented his understanding in the previous work and found that the results he is obtaining match very well with the available experimental data. So that gave a experimental verification of his understanding that the light should be composed of particles, and those particles make the light composed of light quantas. This work was taken up by Einstein, and he introduced the momentum of these particles as n(h) per k. So n becomes integer, so the basic unit is h per k. So from there, it is he introduced that the particles have energy, and they have also momentum at the same time. So these are particles. So light was understood in the form of particles which have energy and a momentum. His work was celebrated in the form of a postal ticket, with the photoelectric effect was celebrated, and it was shown that different wavelengths scatter particles, electrons, and very accurately it was pointed out that the shorter frequency would be having shorter energy, and the larger frequency would be having larger energy, and so on. So, from here we found the basics of basic concept which led to various different devices such as solar cells and solar panels, which we use today. They are based on the photoelectric effect. And then we have everyday life. In everyday life, we have TV remote control, which is again based on photoelectric effect, and we use various different kind of sensors as well. So beyond that, when we wanted to talk about the nature of atoms, so that was also an unsolved mystery, how the electron are really distributed inside an atom. So here the puzzle was resolved by Bohr, and he presented the planetary model of the atom, in which electrons are circling around nucleus, and these are very light particles, and they have proper orbits in which they will rotate around the nucleus, and once they jump from one orbit to the next orbit, they will absorb or emit energy. So this simple understanding was very much useful for various devices which we have today, such as light emission devices, which are used in various different sensors. And then we have X-rays, and the atomic spectrum analysis is also based on this simple understanding of atom. And interaction between the optical field and atom was explained by Einstein, and he coined ideas like spontaneous emission and the stimulated emission. And this was very useful because this modified our understanding of atom and light itself, because light, if composed of light quantas, will be filling the energy gap between the energy levels, and it will be absorbed by the electron to go from lowest to the higher level. And the same light quanta, once the electron is in the higher state, will force the electron or stimulate the electron to come down to the ground state, and will give us an additional photon, additional light quantum. So this simple understanding is now seen later in the development of lasers and also in very recent work to increase the resolution of optical microscopes and taking the resolution to the nanometer scale. So these basic things were so this was all making the first phase or first generation of quantum mechanics, where we have developed the understanding of fields, we have developed a good understanding about the material atoms and how they interact with each other. This got a major boost, this understanding got a major boost from the work of Heisenberg. He published a very seminal work, a seminal paper in 1925. And this seminal paper changed the understanding of entire quantum mechanical world, because in his work, he introduced the idea of superposition and uncertainty, and then matrix mechanics. So this was a major contribution. So the understanding of superposition is quite useful in the development of quantum computers. And then the uncertainty principle, matrix mechanics, they're all very helpful in developing quantum communication, cryptography, and other subjects. So he got a Nobel Prize. He was awarded Nobel Prize in 1932 as with the word that for the creation of quantum mechanics. In the same days, de Broglie came up with this understanding of wave nature of particles. So his idea was simple, that if light can behave like particles, so is it possible that the particle would behave like waves? And he introduced the de Broglie wavelength with this idea. So at a very young age, he introduced the concept of de Broglie wavelength, which was basically the waves corresponding to the particles. So this made, for example, electron moving around a circle, moving around the nucleus in a circle, as if it's a wave which is running around the nucleus in the form of a periodic wave structure. So in that sense, electron behavior around the nucleus appeared to be that of a wave nature, and that wave nature is seen is associated with all the quantum particles which have certain momentum associated to them. So this extended the discussion of wave particle duality, because now particle were also considered as wave. So this simple understanding is very useful in developing various different devices like electron microscopes. And this very recently, this has been used, this wave particle duality is being used in the James Webb Space Telescopes as well. In the same years, Schrödinger came up with his famous Schrödinger equation, and that made all the quantum mechanical puzzles very reachable and given very very simple understanding in the form of the wave mechanics, just as in just like Maxwell equation, but these are for the matter waves. And he also introduced the concept of entanglement when he wanted to talk about the interaction effect of quantum mechanics on macroscopic systems. This generated a furious discussion between Einstein and Bohr. And when they introduced their first article attacking the explanation of quantum mechanics, which is based on probability and the uncertainty principle, and that helped to improve the understanding about quantum mechanics itself. So the entanglement was used as the non-separability of the state mathematically, but in physical nature, this described the correlation between parties involved, and it produces quantum mechanical channels, which are very useful in developing quantum communication techniques and teleportation, or quantum teleportation as it is known. So at the same time, the first computers were made, and they were made based on the vacuum tube technology. So this all was happening completely away from quantum mechanics, but the quantum mechanics helped to improve the basic computer with the invention of transistor in 1947. Because this transistor was used in the manufacturing of these computers, and soon these transistors saw a revolutionary development, and the size of the transistor was reduced tremendously with the help of great improvement in the solid state physics and condensed matter physics. So over the time, with the passage of time, the size of the transistor has reduced, and today we see that this itself is in the regime where we have a single atom transistor and single photon transistors. So light is controlled by light in the single photon transistors. So this very active development led to the shrinking of size of the computers, and then soon we had very handy devices which were seen in our daily life as well. This was, as I mentioned, this was happening because of this shrinking of the size of the transistors over the years, and that was following a non-mathematical Moore's law, and this was happening in the third generation of quantum mechanics, that is between 1950s and 75. That in addition to particle physics, we were having very active development in semiconductor electronics and condensed matter physics. So that helped us in the development of shrinking size of um, uh, transistors and that corresponding devices as well. In the same time, people found that we can test the legitimacy of quantum mechanics itself by using mathematical theorem. And the first came as a Bell theorem, and he introduced in his work he set some inequalities which were required to be met by the quantum mechanical system. And so this was the first work which was helping to understand quantum mechanics on the experimental grounds. With this work, this work was experimentally proved in early 70s. And then we had seen in the same days the development of quantum optics and the development of atom optics, when we found one atom tweezers which were used to control the atomic dynamics in laboratory. So that atom tweezers were very helpful in biology and biological setups. And Arthur Ashkin spent his later years in solving various different biological puzzles. So later work after the understanding of optical fields and the controlling of atoms led to further understanding of cooling our material in the form of atoms to lowest level, and we could bring the atomic temperatures to scales which are never seen in the history of mankind before. So development in the cooling techniques of atoms led the temperature to microkelvin and nanokelvin. And for that work, Cointanogis, Stephen Chu, and William Phillips were given Nobel Prize in 1997. So this work enabled mankind to develop qubits in real experiments, or to understand the necessities, basic necessities to develop quantum computers in laboratory. Feynman advocated the need of quantum computer by saying that quantum puzzles can be solved only by using quantum computers. Later, David Deutsch showed that a quantum computer would be very strong, very helpful, and very fast in solving puzzles. So that with this word came the buzzword of quantum supremacy. So these two gentlemen were quite helpful to convince that we should be having quantum mechanical computers, and our laboratory experiments were very much helpful in devising such qubits in the laboratory setups, which can be used to build a real quantum computer. So in last 25 years, it is possible to see setups where we can handle, or we can have single atom or single photon confinement. So that is basically the building block of a quantum computer in the form of a qubit. So we are in a position to see single qubit and few qubit systems in our hand, and that will be useful to develop quantum computers. It is also possible to assemble quantum circuits in this way, which are useful for various different important quantum tasks. And this is also going to bring us closer to quantum transducers, sensors, and many devices, and a whole new quantum technology in our hands. So this has enabled us to develop the first generation of quantum computer, which is present in various different laboratories at the moment. So various different groups in world are claiming today to have developed first generation of quantum computers. So these quantum computers use quantum bit instead of the conventional classical bits, which were previously used in the case of classical computers. And these quantum computers these qubits can be built by using superconducting qubits. They can be built using trapped atoms or ultracooled atoms, trapped ions or ultracooled atoms. They can also be manufactured using photonic qubits, and then we have topological qubits as well. So these various different candidates are useful accordingly to develop quantum computer in various different setups. So the advantage of these quantum computers is that they are based on superposition, and that superposition concept is bringing us closer to the quantum parallelism. So that is a newer feature which is not seen in the classical computers. And at the same time, in quantum computers, we can see data compression. In conventional computers, in the classical computers, we want to save some information. We want to have the data encoded into the binary form, and for each binary number, we require a bit. So that means that we increase the size of the bits with the size of the data we have linearly. But in quantum computer, this goes exponentially fast. For example, in a computer based on 40 qubits, we can store same size of data which is stored in our conventional computer at hand. At the same time, in our quantum computer, we see that there is no information loss because the qubit control is being done with the help of quantum logic gates. And the quantum logic gates are having equal number of input qubits and equal number of outgoing qubits. So, for example, a control NOT gate is 2 qubit in 2 qubit out gate. So that means we don't have any information loss as well, which is seen in conventional classical computer as well. Major advantage in these systems is the no cloning, or no copying scenario. No copying, it gives a good um, uh, confidence on our computer that data cannot be stolen from a quantum computer. So this is a major advantage, and it's also a very big advantage in developing the data communication or the quantum cryptography techniques. So we know that a qubit cannot be cloned in a quantum mechanical circuit. So this is a very big advantage in quantum devices, including quantum computers. It's based on very low energy loss because there is no information loss, so this leads to very low energy loss. And then we have entanglement, which is only a quantum mechanical feature. And then, as I mentioned earlier, we see also quantum parallelism. So in short, in comparison between the classical computing and the quantum computing, in classical computers, we have classical bits, and in quantum mechanical computer, we have quantum mechanical bits or qubits. In classical computers, we have classical logic gates, whereas in the quantum mechanical way, we have quantum logic gates, which are unitary quantum logic gates. Once we say unitary quantum logic gates, it brings another interesting feature that our quantum circuit is reversible. So that means that we can, if we send our output in the form of input, so we get our initial input return in our hands again. So then compared to classical circuits, we have quantum mechanical circuits, which are based on parallelism. So they're very fast in that sense. And then reading the input bit, we have the measurement of the final state as well. So here I conclude my talk. And if there are any questions, I'm very much happy to answer them. Thank you.
Thank you, Professor Farhan Saif, for a wonderful and very informative talk. So the audience is most welcome to unmute themselves and ask any questions. They can also type in the chat if they have any question. We have very honorable guests in the audience, and especially Professor Asghar Khader is present, who is a very notable mathematician and cosmologist of Pakistan. So, Professor Asghar Khader, if you want to comment. Yes, sir, you have raised your hand. You can unmute yourself and you can speak.
Sir, I want to ask.
I wanted to make a comment. You showed the pictures of Feynman and David Deutsch, but you didn't say anything about them. They were just pictures under something that was totally different.
Well, I mentioned that David Deutsch showed that the quantum mechanical algorithms or quantum mechanical code would be far better than classical codes. So Feynman was advocating that we should have quantum mechanical computers because they will be used to solve quantum mechanical puzzles. We cannot solve a quantum mechanical puzzle on a classical computer. So this was his understanding. And David Deutsch showed that the quantum algorithms would be far better than classical algorithms. So this was big contribution of David Deutsch. And with his work, I mentioned that with his work, the buzzword like quantum supremacy was introduced.
So, Professor Asghar, if the question has been answered, so
Yes. Can I continue or not?
Yes, sir, sure, please.
Okay. My problem with it is what exactly was it that Feynman had proposed? Still not clear. What was David Deutsch's thing? What had he done? What was his idea? I didn't see that it came out at all. So that was my question. Now, if Farhan gives an answer.
Well, I tried to answer your question, and I mentioned that David Deutsch's work was showing focused on the speed of a quantum computer. That it will be far better, far more powerful than a conventional classical computer. So he developed his algorithm. He developed his Deutsch algorithm, where he showed that decision making can be done in a with better efficiency as compared to the in a quantum computer than a classical computer. So I would be
David Deutsch actually is the one who proposed the quantum computer, and there was the idea of how the quantum computer can actually come in. The base of that is with the many world interpretation of quantum mechanics, as it is called. And that is what has led to an actual idea of entanglement. But I didn't see that come out at all in here. So that was my problem with it.
I connected with us with the algorithm. I have focused more on his algorithm, which he introduced, and you're very much correct that multiverse was a important idea coined by him, and that was again very useful in the understanding of quantum computers. But here I presented Feynman as an advocate of quantum computer itself, and Deutsch as uh, uh, as an advocate of quantum supremacy. Using quantum algorithms, it's far better to solve puzzles which cannot be solved or which are very expensive in the classical domain.
Thank you, Dr. Farhan, for the answer, and Professor Asghar for the question. So there was another participant who was going to ask a question. So if you are still here, please unmute yourself, and then we'll also address the question in the chat. So feel free to unmute yourself. Meanwhile,
if I can come in, I saw the chat question. Zafar Iqbal is the one who was asking. And
yes, Zahir
Zafar
Iqbal
Iqbal
has
was
asked.
asking about how the Heisenberg uncertainty principle what the consequences will be in this context. So it's in the chat. So perhaps you could ask him to ask the question.
Yes, how does Heisenberg's uncertainty principle influence the design or future development of modern computer chips and quantum computers?
Well, it's a quite interesting discussion because Heisenberg uncertainty principle also was useful uh, in giving the uh, concept of superposition. So we could see uh, the understanding can be extended to the fine. Here,
Sir, I think like uncertainty principle is at the basis of quantum mechanics. So whatever you do in quantum mechanics, it has to begin with the uncertainty principle.
well, uncertainty principle was definitely as a fundamental concept in the quantum mechanics itself. So, um, so we find when we talk about the development of modern quantum chips or modern quantum computers, so they are based on the qubit concept, and the qubit concept is taking into account the superposition, and the superposition is basically idea is basically connected with the Heisenberg work itself. Uh, uh, um, and the uncertainty principle. So in that sense, we can connect it.
So thank you for the answer again, and I hope Zahid Sab, your question has been answered. So next we have a question by Musharraf Sab. Thanks for the talk, Professor. Based on your experience, what is your number one suggestion for young researchers today? So I would just like to add, like, I think it's a question of general nature, since we are privileged that you are also a recipient of Sitara-i-Imtiaz and Pride of Performance. So we would really love to know that how one can achieve that level of excellence in doing science in Pakistan.
Well, at present, uh, there is a lot of thrill in quantum technologies. There are various different devices, sensors are being made and used in industry, which are coming from the quantum domain. So, quantum computer was a dream some few years back, but today we see that it's very much coming toward common life. So recently, England was making it a big announcement that they are going to connect quantum computers, or they are going to bring quantum computer into our laptops. So this is giving a lot of room for our young scientists, because what is required from them is to train themselves in quantum mechanics. They should understand the applications of quantum mechanics in various different domains, subjects, and then try to see which kind of industry, uh, which kind of specialization they want to have. So I think this is a good time to enter into the subject, because at present we are seeing its connection with the daily life, real applications, and everything is going to be modernized in that sense. So I think younger generation has a good chance to connect itself with the innovation and industry and technology.
Thank you, Professor Saab, and I hope Musharraf Saab, your question has been answered. And there's another question in the chat, and meanwhile we address that. I also see some foreign guests in the participant list. There's Iman Al Umri, so I welcome you also, and you have feel free to type a question in the chat or unmute yourself. And if you want to contribute, we are really fortunate to have you. So in the
Imran
chat,
Saab,
we
I have
have,
a question for
yes, sir,
Dr.
please.
Saab. Thank you, Dr. Saab, for this great, informative presentation. Um, from the perspective of developing economies, what I see right now is that the US and China, they are at the forefront of developing and using the quantum computers at the industrial scale, though the commercial applications are not as much, but still they are using it for various purposes, for space technologies, for drug discovery. There are, of course, other leading economies from the West, particularly European Union, Canada, or the UK, as you mentioned. Uh, if you can help us understand, where does the developing economy stands in terms of contributing to this industry, not just using it, but how do we leverage our research institutions, the infrastructure, so that we are able to contribute to this industry for development, not rather as users as we have been doing, as we have seen in the past. So this is my first part of the question. The second part is, um, um, so once we talk about that quantum computers would be enabled or would be translated into personal computers, how the transition would be, how difficult it would be, or how easy would be the transition, because our entire computing, our data structures are based on classical computers. So would it be a challenge that if we have to translate or transform into quantum computer, the traditional computing infrastructure would integrate well with the quantum computer?
Well, your first question is very interesting. Your both questions are very important. So we can be contributor more than just being users, and that is requiring a will. In our institutions, we should be really focused on um, uh, this prime target, that we want to contribute to the present day technology and want to bring that to our home. So what is missing is that will so far. So we see, as we have been seeing earlier as well, there is a very unique chance to enter into a multi-billion technology which is booming up and growing very fast in everyday development. So there are many countries which are trying to catch the train. India is doing a good. Israel is spending a lot. We have countries like Brazil, South Africa. They are also trying to develop various different kind of industry and also uh, uh, quantum technologies in their own local setups. So we are going rather slow in this direction ourselves, sitting in Pakistan, because and many Islamic countries are also lagging behind in that sense as well. So we should develop our infrastructure. We should develop our curriculum. We should develop our programs very well focused on quantum mechanics and quantum technologies. I would say even to the limit that we should develop universities which are only for quantum science and technology, and training the manpower and the youngster in those places with a focus on the future applications and the future market. So in India, we have one quantum university. It's very interesting. So they have already uh, uh, started this kind of project. So here is something we should be very careful. We should be very serious about. Now, coming to your second question, may I request to repeat your second question?
From a layman term, if you help us understand how easy it would be to integrate the two different worlds of computing. For instance, if we would like to go from traditional classical computers and do the similar operation quantum computing. So how easy it would be to integrate our traditional infrastructure to the more advanced quantum
Right.
infrastructure?
Right. When we want to work with a quantum computer, the approach is different. For example, quantum algorithms are written very differently as we write our classical algorithms. So, so that is again going to require something basic change. The basic change is that we should train our computer scientists, or in our conventional computer science departments, we should convince them they should be uh, uh, flexible enough to understand the quantum mechanical techniques and uh, how to develop how to write quantum algorithms to do various different tasks. Once we have a quantum computer would be requiring a quantum algorithm. And once we talk about the quantum algorithm is written differently from classical computer. It requires unitary operators. It requires concept of uh, uh, wave function, state function, qubits, and so on and so forth. We have to really understand those concepts into our conventional computer scientist brain. So this is, I think, required.
Thank you, Professor Farhan, for the detailed answer. Uh, we will just take a few more questions because we are reaching the limit. So in the guest list, I see Professor Asghari Maqsood, who's a very veteran professor of Pakistan. So, ma'am, if you have a question, you can or comment, you can unmute yourself.
Okay, thank you very much, Farhan, and all the people, you and the other people who arranged this lecture. It was very informative, and especially when a century of quantum mechanics is completed. So I enjoyed the lecture. Thank you very much. Thanks a lot.
Thank you, Professor Asghari. And now I would request Professor Tayyibi, who's the president of ECUSF, for his concluding comment remarks.
Assalamu alaikum. Thank you, my brother Imran Parviz Khan, and thank you for collaboration, IPKI, regarding such events, webinars we have. Right. Okay. Professor Farhan, Saif, thank you for your informative presentation. It is not my subject, quantum physics, actually I'm economist, but was following your presentation and your speech. I enjoyed. Actually, in international trade or bilateral trade, we are borrowing, some terms from physics. For example, we are using gravitation theory, gravitation approach from, physics to promote and to expand, bilateral or multilateral trade relation between countries. Regarding Khalil's question, actually, I would like to know, maybe it is not related, but I would like to know any relation between quantum technologies or quantum, mechanics and gravitation to, to foster any, economic relation in this area. For example, in gravity approach, when we say a bigger GDP, we will have more relation and more, speed of trade bilateral between countries. So the bigger GDP, the more trade flows in this area. Can quantum technology help to this, phenomenon actually? And of course, I'm very much appreciated to your very informative presentation for today.
Thank you for your question. So, there is a whole subject which is named as econophysics. And then once we talk about quantum mechanics and finance, so there is a subject named quantum finance as well, and quantum economics. Professor Skader has written good work in this domain. So once you talk about gravity and quantum mechanics, so in present day quantum technologies, gravitometer is a very important device which is being made, and it is now available with many countries. So this is a device which is uh, even portable at present. You put it in your Jeep in car and take it to one place to other, and then measure the change in the gravitational acceleration g. So that will be helpful. This device is also useful in the space navigation because we have satellite going into the outer space, and the direction of the satellite is measured by noticing the change in the gravity. So this is a very important device, and we have quantum mechanical principles, we have quantum mechanical setups, which are leading us to develop this technology to measure the gravity.
So it can be considered as, a type of facilitation to trade actually between countries, as I understand, regarding quantum mechanics, for example. Thank you. Thank you for that. Thank you for explanation. Yes, Imran?
Thank you, Professor Tayyibi, for your question and for your support. So I think it is a good time so we conclude. So I would request Ms. Hafsa again to provide the concluding information.
Yeah, okay. Thank you, Dr. Saif, for your time and your insights. And before we wrap up, we encourage all the attendees to take a moment to fill out our feedback form that I just sent in the chat to ensure that you receive a participation certificate. Once again, thank you all for being with us today, and we look forward to seeing you guys again in the next session of Science Chronicles. Till then, stay curious, keep exploring, and have a wonderful day ahead.
So thank you, Professor Saif. Once again, it was pleasure having you, and I would request to stop recording.